What's the determinant of a 61 by 61 matrix? I can tell you it's 1. In my head, no calculator, because this matrix has a secret. It's a tridiagonal matrix of ones. Ones on the main diagonal, ones on the diagonals just above and below, and the zeros everywhere else. The determinant of this family follows a pattern that repeats every 6 steps. The values cycle through 1, 0, -1, -1, 0, 1, and then back to 1 again. Since 61 mod 6 equals 1, the determinant of the 61 by 61 case is exactly 1. Let me show you why. A tridiagonal matrix has non-zero entries only on 3 diagonals: the main diagonal and its 2 immediate neighbors. Our family, a sub n, places 1s on all 3 of these diagonals. A sub 1 is simply the single number 1. A sub 2 is a 2 by 2 matrix where all 4 entries are 1. A sub 3 is 3 by 3, ones along the main diagonal and the adjacent diagonals with zeros in the 2 corner positions. A sub 4 extends the same pattern to 4 by 4. The structure is always the same. A narrow band of ones running through the center of the matrix with zeros filling everything outside that band. This pattern continues for any size n, defining an infinite family of matrices. Start with the determinants of the small cases. The determinant of A sub 1 is simply 1. For A sub 2, the 2 by 2 formula gives 1 times 1 minus 1 times 1, which equals 0. For A sub 3, we expand along the first row. The first entry, 1, carries a positive cofactor sign and multiplies the 2 by 2 minor from rows 2 and 3, columns 2 and 3. Now that block has entries 1, 1, 1, 1, so its determinant is 0. The second entry, also 1, carries a negative cofactor sign and multiplies the minor from rows 2 and 3, columns 1 and 3. That block has entries 1, 1, 0, 1, giving a determinant of 1. The third entry in the first row is 0, so it contributes nothing. Putting it all together, the determinant of A sub 3 equals 1 times 0 minus 1 times 1 plus 0, which gives 0 minus 1 equaling -1. Now, the pivotal step, we expand the determinant of A sub 4 along row 1. The entries in row 1 are 1, 1, 0, 0. Since the last 2 entries are 0, they kill the last 2 cofactor terms entirely. Only 2 terms survive. The first term comes from the entry A11, which is 1 with a positive cofactor sign. Since -1 to the power 1 plus 1 is positive 1. We multiply by the minor obtained from rows 2 through 4 and columns 2 through 4. That submatrix is exactly A sub 3. The second term comes from the entry A12, which is also 1, but this time with a negative cofactor sign. Since -1 to the power 1 plus 2 is -1, the corresponding minor uses rows 2 through 4 and columns 1, 3, and 4. That gives us the 3 by 3 matrix with rows 1, 1, 0, then 0, 1, 1, then 0, 1, 1. Notice the first column of this minor is 1, 0, 0. Expanding down that column, only the top entry contributes, and it reduces the calculation to the determinant of the bottom right 2 by 2 block, which is exactly A sub 2. So we arrive at the equation determinant of A sub 4 equals determinant of A sub 3 minus determinant of A sub 2. Plugging in our previously computed values, that's -1 minus 3, which equals -1. This argument wasn't special about 4. For any n, row 1 of A sub n reads 1, 1, and then all zeros. So cofactor expansion along row 1 always yields exactly 2 non-zero terms. The first non-zero term comes from the 1, 1 entry, and it gives us +1 times the determinant of A sub n minus 1. The second non-zero term comes from the 1, 2 entry, and because of the checkerboard sign, it gives us -1 times the determinant of A sub n minus 2. All remaining terms are 0. So the general cofactor expansion reads determinant of A sub n equals +1 times determinant of A sub n minus 1 plus -1 times determinant of A sub n minus 2 plus 0 plus dot 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 plus 0. Simplifying, we get our boxed recurrence. Determinant of a sub n equals determinant of a sub n minus 1 minus determinant of a sub n minus 2, valid for n greater than or equal to 3. Notice this looks a lot like the Fibonacci recurrence. F sub n equals f sub n minus 1 plus f sub n minus 2, but with subtraction instead of addition. Let's run this recurrence and compute the values one by one. The determinant of a sub 1 is 1, and the determinant of a sub 2 is 0. These are our starting values. Now, the determinant of a sub 3 equals the determinant of a sub 2 minus the determinant of a sub 1, which is a 0 minus 1, giving us negative 1. This matches our earlier computation. The determinant of a sub 4 equals the determinant of a sub 3 minus the determinant of a sub 2, which is negative 1 minus 0, giving us negative 1. So the determinant of a sub 5 equals the determinant of a sub 4 minus the determinant of a sub 3, which is negative 1 minus negative 1. That's negative 1 plus 1, which equals 0. The determinant of a sub 6 equals the determinant of a sub 5 minus the determinant of a sub 4, which is 0 minus negative 1. That's 0 plus 1, which equals 1. The determinant of a sub 7 equals the determinant of a sub 6 minus the determinant of a sub 5, which is 1 minus 0, giving us 1. Now look at the full sequence. 1, 0, negative 1, negative 1, 0, 1, and then 1 again. Position 7 matches position 1, and the position 8 would be 1 minus 1 equals 0, matching position 2. The sequence repeats. The cycle has period 6. Why must the sequence cycle? Each term depends only on the two terms before it. Every determinant in this sequence is negative 1, 0, or 1. That's just 3 possible values. So consecutive pairs can take on at most 9 combinations. By the pigeonhole principle, a repeat is inevitable, and once a pair repeats, the recurrence locks the sequence into a permanent loop. Let's see this concretely. At position 0 and 1, we have the pair. Determinant of A0 equals 1 and determinant of A1 equals 1. Here, we define the determinant of A0, the empty matrix, as 1. Now, at positions 6 and 7, we get determinant of A6 equals 1 and the determinant of A7 equals 1. That's the same pair. So the sequence repeats from that point onward. The period is 6, guaranteed by the pigeonhole principle, not coincidence. We can visualize this as a hexagonal cycle wheel. 1, then 0, then negative 1, then negative 1, then 0, then 1, and back to the start. The sequence cycles endlessly through these 6 values. Back to the opening question. What is the determinant of A sub 61? The sequence of determinants repeats every 6 terms, so we just need to compute 61 mod 6. 6 goes into 61 10 times, since 6 times 10 equals 60, with a remainder of 1, so 61 mod 6 equals 1. Remainder 1 points us to the first entry in our period 6 cycle table, where the determinant equals 1. Therefore, the determinant of A sub 61 equals the determinant of A sub 1, which equals 1. No row operations, no cofactor expansion, just one division and a table lookup, and we found the determinant of a 61 by 61 matrix. This is a powerful strategy. Exploit structure before you compute. Let's review the entire journey. We started by recognizing that our matrix had tridiagonal structure, non-zero entries only on the main diagonal and the 2 adjacent diagonals. The tridiagonal structure collapsed an n by n determinant into a simple 2-term recurrence. D of n equals D of n minus 1 minus D of n minus 2. Then we discovered that this recurrence is periodic, cycling through the values 1, 0, negative 1, negative 1, 0, 1, and then repeating every 6 terms. Finally, modular arithmetic gave us the answer instantly. 61 mod 6 equals 1, so D of 61 equals D of 1 equals 1. Tridiagonal systems appear throughout applied mathematics, in numerical PDE solvers, signal processing, and quantum-tight binding models. The same cofactor to recurrence technique applied with other diagonal values generates Chebyshev polynomials. A 61 by 61 determinant solved with one line of modular arithmetic. That's the power of seeing the pattern inside the matrix.